Okay, so this is my Minecraft computer, or CPU, I guess. I don't know. I don't know. I think a computer needs other stuff besides a CPU. But, anyways, I'll go around and show you the components. So this one is the ROM, and it's where you put the assembly, basically the instructions. So as you can see, I have all these repeaters here. So this is the program counter, and this is the program counter is 8-bit, and the ROM is 16 by 16. So currently there's 256 basically lines of assembly you can have, and what you can do here is you can clear the program counter, and then this will increment it, so it'll go up and select it. So how this works is there's the horizontal, the 4-bit horizontal, and 4-bit I guess you could say vertical. It's kind of like X and Z because it's flat, but you know. And then these are AND gates. This is just a line of AND gates that goes under. So here you can see the Z line and then the X line. And then what this does is it just powers this, which, see, if I go here and if I were to clear the thing, so it'll go back to 0. It'll select the first one, and as you can see, these lights light up because these are the repeaters that are in place. So if you were to rotate the screen, because you know how binary goes from like the highest bit value is on the left to the right, so like decimal. If you were to rotate the screen 90 degrees counterclockwise, then this would be in order. So this is the first bit. This is 1, 2, 4, 6. No, 1. I always do that. I always start counting in twos. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, 2048, 41, 50, yeah, whatever. But so basically, then this is just a line of repeaters that goes out into here. Okay, so this is the ROM, and I guess I'll show you the other components. This is the RAM, and they're all the magenta stuff, and it's 16 total registers, but only 2 are reserved for other things, and so 14 are the actual ones that programs can use. This is just a display I made that has basically a register right here that can load a value into it. This is the ALU. Currently, you can only add and subtract. Technically, well, we don't have jump instructions yet. I'm making those in a second. But technically you can, because you can do multiplication by, of course, adding multiple times, or you can actually do division with subtraction by, if you want, let's say you want to divide 100 by 3, you would, I think this only works with whole numbers, like whole with no remainder, but if you wanted to do like 100 divided by 2, you would subtract 100, or you would subtract 2 from 100 until it equals 0, and then that's your answer. And then the number of times you subtracted is your answer. So it would be 50, because you subtract 50 times. So that's just a neat little trick. So once I have like if 0 things, or if whatever, then I can do that. Next is, well, that's basically it. Oh, we also have the clock right here, which is a hopper loop. Oh, there's also the instruction decoder, basically. So the bottom 4 bits are always for the instruction, and that goes to the instruction decoder, and it can select the instructions. So we have load number, jump if 0, jump if greater than 0, add, subtract, multiply, divide, right shift, NOR, XOR, not, and display and halt. I'll explain all these. So I'll explain the ones that are implemented. So load number, what it does is it lets these values through. Here, well, actually, I'll just read this out. So load number, it takes in the nibbles of the. So currently the ROM is 16-bit, and instructions take up 4 bits. So that leaves you 12 bits for numbers. There's no really reason why they're not. We could make this infinite bits, basically, and there wouldn't be a reason to not do that. But I don't know. I don't remember why. But so there's 12 bits for the numbers. So that's the top 12 here. So when it loads it into the first register, which in the assembly is called LReg, which is load register. So what this does is it runs this, and then it opens this. Basically allows the data, the 12 bits, the top bits, to go into the RAM input, the write lines, and then this lets this makes sure that this data isn't interpreted as a register, an input register, because what this white one does is it selects these are the two read selects, because this is dual read RAM, and this is the write select. And so currently write is off, or it should be, I guess, I'm not doing any instructions right now, but so this would be 0, it will be all off, so that would select register 0 or register 1 if you're not doing 0 indexing. So there's the first register, and then it sends out a write signal, which is blocked until the clock hits its signal, and then it sends over the 12 bits of data. So these are on. So if I were to run it, actually, let me turn on the clock. Okay, so see, if I run this, the program that's in there right now loads two numbers, moves them around, and then it does some math. So right now we're on the first instruction, which is written in here, and so it's on load. So this is blocked off. No data can go through here, but this data can. And so here's the write stuff, the write lines. So this is the number that's in here, in the write lines, and then you can see this write signal is being blocked by the clock. So the reason why we have the clock is so it doesn't like if you had the ALU adding something and it was just always on, it would act as an incrementer, and it would just keep adding the same thing over and over, which isn't very easy to control if there's all repeaters and stuff. So I can click clock step, and it'll step the clock, set in the right input, and then it'll automatically switch to the next instruction, which is a move instruction, which actually, instead of implementing that whole thing, what we did is just use the add instruction and add the second register, which is an empty register, so it's just all zeros. We add that to the register we want, and we output that to whatever register we're going to move it in. So that's just a little. So when you write the code before you put it in the compiler, you use a move instruction, but it compiles as an add instruction because it's just, simpler to do things simpler, I guess. So this is the same. It's the same data that was there, but it's moving it from the first register into the third register, which is data register 0 for the program space. So here you can see the write line, and then the second one is selected. This is 0 index, so it's the third one. As you can see, 1, 2, 3. This one's on. And we just have to wait for the right signal. So I'll stop the clock. There, it's written. And then the next instruction is to load the second number. So as you can imagine, it'll load the second number. Boom. Then it'll move the second number once we get to that spot. Okay. And then it will subtract them. So the subtract signal is this one. It takes in the first register and the second register and then the destination register. And this line basically just activates the ALU. That's this whole thing. And then the subtract line also follows it and turns on the subtract flag in the ALU. And so as you can see, the dual read is working right now, where we have this one selected. So remember, this is the first number because it's the third register, and this is the fourth register. And then the dual reads outputs go here and here. That's why there's two sets of these. So that's why it looks like a symmetrical. This is where the right lines are connected, is because there's basically twice as many registers in the RAM, but they are all duplicated. So as you can see, there's two different numbers going to the ALU. Subtract flag is going, and then it outputs to the ALU right buffer, or whatever you want to call it, and that goes into the right line. And then as you can see, there's a right signal waiting to be activated. Clock step. There we go. So now the data is stored in register 5, I think. I'm pretty sure. But this is I'll clear this real quick so you can see it change. So the last instruction is the one that loads the register, or displays the number. So as you can see, display is on. So this travels way over here, and it goes over here, and it activates. This is the read line, by the way. I didn't explain that. But this is both connected. It just turns on the output from the registers, basically. So this goes over here, and there's also, so the read line from the second dual read always goes here, but it's blocked by this register for it. Oh, did I not? Oh, I didn't clear it because the input was already that. So I will real quick reset this manually. Okay, so it's those zeros now. So as you can see, the input's going here, and then this is the flag this is the signal that writes the data to the registers, and then as you can see, it is blocked by the clock, or it has to send a clock signal. And what this does is, if the display signal is off, then this will be on. It'll block any calls that go there. But if it's not, then I can step the clock, and if you watch closely, there you go. The data is written, and then there's our answer. Oh, also we have fireworks that go off when it's halted. So, okay, and the last one is the halt command, which is pretty simple. It goes over here, and basically all it does is it stops the clock. It's just a simple little circuit this is the button that starts it and stops it. So yeah, that's basically it for now. Currently, the only instructions we have are the add, subtract, load number, halt, and display. So there is stuff you can do with it. It's not very I don't think I think you have to have conditionals to be Turing complete. I'm not sure, but it's close. It's really easy to add those. I've just been kind of lazy. Yeah, there's lots of different prototypes and stuff around here, different parts for the thing. It's a pretty big world. This is an old version over there, 8-bit. But this one we put together, me and my cousin put together in about 4 days from scratch. Well, we still had the. I think all of this is new. I don't think we reused anything from the old ones, but it's the same basic principle for everything. The repeater locked registers, which work really good, and there's the read line with the subtracting comparator. So it's all pretty simple. You know, I have this thing. If I'm explaining this stuff to people, I tell them that making a computer is very easy. Okay, let me say that again. The hardest part about making a computer is either working with electricity, or in this case, building it in Minecraft. Because making a computer with just logic gates, like if you ever go to a logic gate simulator and you can do that, it's so easy because you don't have to deal with, well now, because we have the itty bitty little transistors, is the quantum stuff. But just electricity in general, I don't really get. I of course I've done stuff with it, but I don't really understand all the voltage and stuff. I'm pretty sure voltage is like the speed of the electrons, and then amperage is the kind of volume. I've heard the water expression before, like pipes. But yeah, pretty simple. If you ever thinking about building a computer, definitely should. It's very good to learn how things work in the world. In case, you know, the apocalypse comes, maybe there's a solar flare and all the computers are wiped out, and you find some vacuum tubes. I don't know, maybe you can build a little calculator. But yeah, works pretty good.